life cycle assessment, also known as LCA, addresses the environmental aspects and potential environmental impacts throughout the product's life cycle, from raw material acquisition through raw material extraction, production, use, final disposal, or end-of-life treatment. Therefore, it covers the entire life cycle, from cradle to grave or cradle to grate, when the impacts after the manufacturing process are not considered. With the LCA, it is possible to determine the environmental hotspots of a product or process, and to use this information to improve the environmental performances at every stage of its life cycle. Based on the definition provided in the ISO 14040, the LCA method consists of 4 phases: the goal and scope definition, the inventory analysis, the impact assessment, and the interpretation of results. LCA is a decision-making tool, often used for the development of environmental planning, business strategy, product or process design, and marketing, as well as many other applications. The LCA models the life cycle of a product by studying the product system within specific boundaries. The system boundaries needs to be defined in the framework of the product life cycle. According to the EN standard 15978, the life cycle of a construction product is divided into modules. As shown in the picture, the modules are: Module A covers the manufacturing stage of a product or materials at the construction of the building. Module B covers the use and maintenance phase of the product. Module C includes the end-of-life operations such as demolition and disposal, and then Module D, which includes the circular economy practices such as reuse or recycling, which are located beyond the system boundaries. Each module contributes to the overall environmental impact of glass to a different extent. The stages A1, A3 are associated with the highest environmental impact over the glass life cycle. In a cradle-to-gate analysis, the stage A1, A2 account for approximately 40% of the global warming potential associated with flat glass. These stages include the extraction of and transportation of raw materials such as silica sand, soda ash, dolomite, and limestone. Then the manufacturing alone contributes about 50% to the total global warming potential. Glass production is an energy-intensive process requiring between 6 to 8 gigajoule of thermal energy. This energy mainly comes from natural gas or fuel oil used to heat up the glass furnace to the high temperature required to melt the raw materials, which is around 1500 degrees. The manufacturing process of flat glass is an energy-intensive, involving melting raw materials at high temperatures. Therefore, this stage contributes to the largest share of impacts. The packaging and transport of the final product have a smaller impact compared to the production and raw material acquisition. The end-of-life stage can vary depending on the scenario applied to the post-consumer glass waste. The current scenario involves landfill for the majority of the glass waste. Nevertheless, recycling post-consumer cullet has a high potential for reducing the glass impacts. Studies indicate that increasing the recycled content in the furnace can contribute to the reduction of the energy needed for melting the raw materials. It's estimated 2 to 3% reduction of energy consumption per 10% cullet in the batch. The CO2 emissions, and in particular the process emissions, which cannot be reduced by switching to carbon-neutral energy. In the first phase of an LCA, all general decisions for the setting up of the analysis are made. In the goal definition, the reasons of the study are defined, as well as the target group of the study, and also whether the analysis will be used to compare systems or products. In the scope section are also included the product description, the study assumptions, the system boundaries, the functional unit, the methodology, and the data quality of the study. When defining the system boundaries of the study, all relevant life cycle stages shall be included as far as possible. For example, a cradle-to-gate system for the glass products includes the extraction of raw materials, sand, soda ash, and limestone, and the energy required during the transformation of these raw materials. and during the float production process, as well as the transport. After defining the processes included in the system boundary of the study, all the elementary flows, as resources and emissions, crossing the system boundaries should be recorded. After the goal and scope definition, the following phases are the life cycle inventory and the life cycle impact assessment. The life cycle inventory is an inventory of input and output data related to the elementary flows of the system under study. The life cycle impact assessment aims to describe the impacts caused by the emissions and consumption of resources over the whole life cycle. This is achieved by aggregating the inventory results into selective categories according to the type of environmental impact they contribute to. For example, all emissions of greenhouse gases may be aggregated into one indicator for climate change, and all acidification emissions can be aggregated into one indicator for acidification, and so on. The number of impact categories evaluated in this phase comply with what is specified in the goal and scope. The results from a product life cycle assessment analysis typically set the content of an EPD, so an Environmental Product Declaration, which is a verified document. EPDs are used by organizations for communication purposes, and unlike the LCA, they do not contain sensitive company details or product information, such as the bill of materials. EPD reports are verified by independent party, which guarantees the quality of the data, the application of the standards, and application of the specific product category rule. The EN 15804 is the core standard for the EPD certification of construction products. The product category specific rule for flat glass products are set in the EN 17074. Here there is an example of EPD certificate from the company AGC Glass Europe. This EPD refers to an 8 mm thick soda lime glass. In order to be able to read and correctly interpret the data in the EPD, it is important to look at the following parameters. The functional unit of the product, so the quantity of material being studied. In the glass case, it is often 1 square meter of float glass used in construction for a lifespan of 30 years. The modules of the life cycle not included in the analysis because irrelevant for the product or because the manufacturer decided to not include them in the analysis. In the glass EPDs, certain phases related to Module B are typically omitted. The system boundaries of the LCA, so if it's cradle to grave, or cradle to cradle. And then the environmental indicators that we want to consider. The global warming potential, the acidification potential, the ozone depletion, the eutrophication potential, and so forth. This lesson explored the life cycle assessment method and its role in evaluating the environmental impact of glass. It explained the main LCA phases, system boundaries, and key impact areas, with a focus on the environmental footprint of glass production. It also highlighted how recycling cullet helps reduce energy use and emissions, and the importance of environmental product declaration, EPDs, for communicating environmental data. Understanding these concepts is key to driving more sustainable glass production and use.